Okay, let me get started. Thank you everyone for attending the fourth session of our monthly webinar series with the theme of generative AI. In the previous session, we presented the pipe design agent, which is a practical application where an AI agent is used to parse a design guideline, answer to engineering questions, and execute different engineering calculations. This session, we will explore another application of AI agents, this time in the field of synthetic data and simulation engineering. So although it sounds technical, but even if you're not technical, you're not familiar with some of these terms like finite element analysis or synthetic data, still you can get a 90-95% of the whole thing that we're going to cover, because we want to talk about the agentic workflow. And this is just one application of that. And the same concept could be applied in your application, in your own industry. So we will demo the finite element analysis assisted agent. So FEA stands for finite element analysis. So this is a simulation or numerical technique in order to model and solve the problems in engineering numerically. Where an AI agent is used to create a finite element model, run the model using Abaqus, which is one of the leading finite element softwares. And we also post-process the results after being generated. And also we do a parametric study where we run the subsequent steps based on what's been retrieved. So we will basically showcase a live demo, and you will see how it goes. Before getting into the slide deck, first let's have a brief introduction to Arcurve, which hosts these monthly webinars. Founded in 2006, Arcurve is a full-service technology, advisory, and software development company. It guides organizations across different industries on their data journey, helping them leverage technology to enable data-driven decision-making capabilities. So, just a quick bio from my end. I am a lead data scientist at Advanced Analytics Groups at Arcurve. And by training, I hold a PhD in civil engineering from Memorial University of Newfoundland, which was focused on the stress analysis of subsea pipeline. So there's no surprise that this session and the previous session are around pipeline. I might be a little bit biased, but as I said, so all these is more about some of the applications of agentic or AI agents, and it could be applied in different industries. As an industry experience, I have about 7 years of experience in various fields or industries in building machine learning and large language model applications, especially more recently focused on large language models, and doing finite element analysis and numerical assessment, especially during my research time, and also doing pipe stress analysis. And I've worked with TechniFMC in St. John in the Advanced Analytics Group, and I also work in Northland Press and in Calgary. And then when I transitioned into tech, I worked at AutoML, and now I've been working at Arcurve for about 2.5 years now. And in my personal time, I spend most of my time with my family, and I enjoy playing ping pong, mountain climbing, traveling, and making and eating sushi. And I pass it over to you, Mike.
Thanks. I also have a background in engineering from Waterloo, geological engineering originally, but I have spent most of my career working in this sort of hybrid domain of applying various technologies and algorithms and whatnot into engineering-centric use cases. I'm going to speak about actually some of that today in the session, as I did have a lot of experience in the mining industry, in particular applying technology and three-dimensional modeling methods and finite element analysis methods and whatnot to solving various mining challenges, which is germane in the context of this session. I also worked in the environmental domain for a number of years, and then founded a company called Menome Technologies in 2016, we created a product that was designed to simplify integrating complex data sets for building models, for modeling physical systems and deriving insights for that. That company was acquired by Arcurve in 2020, and these days I act as an advisor on various AI ML projects and insight generation projects. And I speak with a lot of audiences on the subject in non-working related things, lots of mountain biking and skiing and whatnot. But more recently, been having quite a bit of fun playing in the band with my daughter. And if anybody's in town this weekend, we have a show, so you can check that out.
Nice. Yeah, I would certainly recommend going there. Unfortunately, I'm not in town. And let's go to the next slide and talk about the agenda. As for the agenda of this presentation, we will start by discussing the business challenges that enterprises face, as well as the benefits they can gain from leveraging AI agents. We will also provide an overview of the transition from manual drafting tools to simulation models, and more recently to agentic workflows for doing engineering tasks. Next, we will briefly introduce a specific type of AI agent called a React agent. For those of you who have been following the webinar series, it's just a quick reminder, and we won't go into the details. Finally, we will showcase, as promised, we'll showcase the Finite Element Analysis, or FEA assisted agent, which is an advanced application of React agent in simulation engineering. With that, I hand it over to you, Mike, to discuss the business case for leveraging agentic AI.
Thanks. Yeah, so as mentioned, when I started my career, I'm old enough that when I first went up to the mine sites, and I worked across quite a number of mine sites all over Canada, this was typically not necessarily black and white. They were actually in color. But this was typically the setup that they had. All the work was done by the mine engineers and the geologists on Mylar tables. So you had a lot of the engineers and the geologists and whatnot at that time were spending a great deal of time just drawing and maintaining the plans physically. And at that time, so this was in the late 1980s, early 1990s, personal computers and three-dimensional modeling tools had just become available. So I was really fortunate while I was at Waterloo University, I got connected into what they call the Advanced Mine Integrated Mine Design Modeling Project at a place called the Noranda Research Center in Montreal. And if you go to the next slide, which was amazing because they had all of these, advanced machines at that facility. And what they had undertaken was the realization that they had a team at the Noranda Research Center that was set up to do various different types of numerical analysis and on the mining operations and help out with the designs of the mines and whatnot, optimizing them and that kind of thing. But it would take months for them to take the Mylar plans and manually build these into the three-dimensional models that were required as inputs to the finite element models and other tools that they had available at that time. So what the team and myself at that time did is we started writing software inside of low-cost systems like AutoCAD, which had just become available around that time with its 3D extensions, to enable the mine staff, to the geologists and engineers at the mine, the surveyors at the mine sites, to actually construct and maintain their own three-dimensional models. The parts that I contributed to that effort were known as BlastCAD and the section cutting systems. So I ended up working and deploying those systems across, I think 7 or 8 mine sites across Canada through the course of university and afterwards, which was a pretty incredible experience. Because you'd literally go to the mine site and they would have Mylar, and the job was to set up, build all the models and everything else, get that all established, teach the staff how to use the tools and whatnot, and then provide feedback to the engineering teams. But the important part of that was the fact that reduced the cycle times between something happening at the mining operation and then the advanced engineering analysis to be done in a much more quickly. So in one example here, specifically with this thing called BlastCAD, what we were able to do was the thing that you see on the right there, the model of the mining operation. The software itself allowed the mine staff to actually construct their own sections that they would then do blast design layouts on. They could also then hook that up to a special program called CPF-CAD, or Cell Powder Factor Analysis, which was a numerical modeling program that actually did what they call cell powder factor calculations on the blast. It helped optimize the blast design. So then the blasting engineers at the site, instead of having to send all this stuff off to the folks at the Noranda Research Center and waiting weeks or sometimes months to get the results back, they could do it at the operation on site the day of or the day before they would send the blast designs down to have them actually constructed in the mine. And they could optimize those designs by laying the design out, running it through the cell powder factor analysis, and then having that information come back into the model. So if you go to the next slide, the really critical piece of this, though, you'll have to hit next again. I think I missed one transition. There we go. Perfect. What this did is this enabling the mine engineers and geologists to create and maintain their own unified mine model accelerated the mine design process by reducing and eliminating a lot of this manual work. So then we were able to much more accurately and rapidly provide engineering design insights to the folks at the mine site, which improved the mine designs, which improved the safety, which reduced cost, because they could actually iterate on the designs and complete them much more quickly than they could prior to that. If you go to the next slide, the other thing this also enabled that was quite revolutionary at the time was when a failure happened. So this is an actual real use case that happened at the Hemlo Gold Mine when I was there. The East Ore Pass, which you see in that cyan color in these models, and you'll notice the renderings are pretty blocky. This was sophisticated at the time. It would take almost 3 hours to render that output, which is funny when you look at it now. But this unified mine model at the mine site, what this let us do is we were able to then take a LiDAR, an early version of a LiDAR survey instrument, put it into this ore pass. So what had happened is that cyan area that you see is an ore pass, and it had failed. And what happens is as it fails, it expands outwards and starts threatening the red and the green areas, which are the drifts. They're the things that you walk around if you're in the underground mine. So this is a pretty serious problem. But by using a combination of the unified mine model at the mine site, we were able to shoot a point cloud. And then I wrote a program that turned that into an envelope and another program that ran sections through it. And then we were able to feed that into the finite element programs to do the stress analysis to figure out how to reroute the mine workings to avoid this failure, and then also how to safely direct drills into filling up this particular failure with shotcrete and other sorts of mitigated measures so it didn't get worse. And this was incredible. We were able to do this at the mine site so that this failure was mitigated much more quickly than would have been otherwise possible. Revolutionary stuff. So if we go to the next slide. Now, our ability to build these 3D models since that time has improved massively. Like the models that we can make now of complicated systems, and these are just various, building information management systems. Another one's from Myra Giro's GoCAD implementation, Myra Geosciences for doing complex three-dimensional mine and geological modeling and whatnot, compared to the stuff we had back in the 90s when I was doing this sort of thing actively. This has improved immensely. But if we go to the next slide, the number of tools and systems and things that we use to run a typical engineering have literally exploded. So, for example, in the architectural domain, which is a parallel domain to where a lot of this sort of numerical modeling and design, three-dimensional mine design or three-dimensional modeling capabilities are applied, have increased exponentially. So on a typical BIM project, it's not uncommon to deal with 30 to 50 systems and data sources just to work on this project. And what this has meant is we've now ended up, ironically, back in a similar situation to what we were back when I was working in the mining industry. So if you go to the next slide, the complexity associated with getting the data out, even out of a relatively simple database, such as the one I've shown here. This is an environmental database. Now imagine the number of different databases that go into any sort of analysis these days. And this is from a study that was done recently. Companies are drawing from 400 different data sources on average to feed business intelligence and analytics. And that's just simple stuff. We're not even talking about complicated things like numerical analysis here. If you go to the next slide, What that means is that the engineers and scientists and folks who do this sort of analyses, these numerical analysis or otherwise, they're spending most of their time doing manual work again. Instead of drawing things on Mylar plans like we used to have to do, they have to manually pull data from all of these different sources, put it together, set it in the right form that goes into the finite element analysis tools or other things that are used to do these sorts of engineering, predictive analyses and computational analyses, run those things, get the outputs, transform them back into a form that can go back into the design software, often by hand, run them again, put them back out. So this becomes an incredibly time-consuming process. So this is where, when we think about this world of agentic AI and the examples we've shown so far through the course of our series here, what starts to become possible is that the agents are now smart enough and capable enough that they can do the lifting in terms of being able to pull data from these different places, handle the transform of the data into the forms that are amenable or needed to actually run types of numerical analysis. And they can also make adjustments from the outputs coming back out of the systems to then rerun them again. So what ends up happening is similar to the way that we made the cycle times associated with design and insight and decision back in the day when 3D first came into the picture. We now have the ability to apply agentic AI systems or approaches and methods to this challenge around working with distributed, complicated data sets in a very dramatic new way. And if you go to the next slide, what this does is agentic AI addresses this complexity. So it's going to and will allow us to streamline engineering workflows by bridging the design and analysis, by coupling, allowing us to essentially turn systems like the one Farhad's going to show you today into tools by registering them in the context of an agentic workflow. So then the engineers can go, here's the criteria that I want to try and meet in terms of my design, and then provide that to the agents, which then determine which of the tools they need to run to perform these analyses. The agents can then also map the criteria from the forms that they're in into the form that the tool needs to execute it, take the outputs from those tools, inspect the results, tune them and optimize them as per the criteria given by the engineer or the designer, run them again until they converge to a set of predefined conditions that the designer or engineer has provided, which then allows us to dramatically reduce the cycle times required to produce design outputs and explore options and all of these sorts of things. So again, as in the case back when we were doing the 3D thing at the mine site with respect to the East 4 pass failure, we can now much more rapidly move through design options to get to a result that then can be implemented in the engineering context. If we go to the next slide, the other thing that Farhad is also going to talk a little bit about today and illustrate is this notion of augmented training data, and you may have to click run on that video. So something else that becomes very interesting, and this is a bit of a new capability, and this is something that's just happened in the last few months, in fact, is that companies that do things, and this is an example of a company called Physical Intelligence that is applying large language models to the domain of training data. So robotic systems in this case, which is what this illustration is, have been constrained and limited by the fact that there's only so much information or data available to use to train these things. So you can use large language models, combining them with the types of inputs that these types of systems and also engineering design systems and whatnot to generate synthetic data for them to increase the amount of data that they have for training these things and making them smarter and more capable. And you're going to see this accelerate the capabilities that these types of engineering systems, design tools, and of course, robotic systems and whatnot have massively, I think, fairly quickly. And if you look up this Physical Intelligence company, this is a really good example of exactly that. So now I'm going to hand it over to Farhad, who's going to show you the real world example of this being, of the agentic workflow being applied to the engineering, design, and finite element analysis use case.
Okay, let's go to next slide. Thank you very much, Mike. That was a fantastic overview of this transition from where we were and where we are heading toward. And you set the stage again for me to go through the next slides very well. Just before getting into the specifics and the demo, I would like to first talk about what is AI agent. And then we will talk about the React agent, and we will go toward the like showcasing the demo. As for what the AI agent is nothing more than a large language model with a specific set of instructions. For instance, you can have GPT-4o or Claude 3.5 Sonnet, and you can provide set of instructions like, whenever I ask you a question, I want you to break it down into smaller pieces and then solve it sequentially. I mean, that could be like one set of instructions. And in addition to that, these agents typically have memory and tools. So as for memory, because if they need to solve some problems sequentially, they need to remember what was going on in the past. And they should, for instance, remember what was the original query so that at the end, they can address the original query that was submitted by the user. And in terms of tools, this is like what Mike mentioned. So these tools could be the application, the softwares, or like a Python function that you basically develop. The main thing is that you have full control and you have the full flexibility to manipulate and manage these tools. So with that introduction, I'm going to talk about a particular application of a specific agent or AI agent that we call it React agent. So React stands for reasoning and acting. Like I said at the beginning, for you that you have been following, you might be familiar, but I just want to quickly go over the React agent and introduce that for some of you that you might have not been in the previous meetings. So, and the reason that we are advocating for React agent is because for using the generative AI or this AI agent at the enterprise level or in the business process, two challenges that we typically have are transparency and accountability that are provided by this React agent that we will see quite quickly. But so in terms of React agent, so it stands for reasoning and acting. So reasoning effectively means that it breaks down the problem into smaller parts, and it uses chain of thought to address each part or to address the parts step by step. For instance, if the goal, like what you see in the flowchart, to get from point A to point D, what it does, it goes from point A to B and then B to C and finally C to D. It tries to tackle each segment individually and fit the results of the previous segment into the subsequent one. The key aspect of the reasoning is that each part of the problem is not solved by the large language model or by its training data. Instead, it's been solved by a particular tool. So each part of the problem has been mapped to a specific tool, which is something that large language models are pretty good at. And then so the React stands for reasoning and acting. And in the acting part of the React, what it does, it executes these tools. And the results of that would be effectively what we call it observation, which will then feed into the next step. So again, we break down the problem to smaller pieces, map it to different tools, which is what agent does. And then those tools are executed and the results are fed into the next step, which is what AI agents are pretty capable of, and they do. We just need to provide them with the tools. And that's why this approach adds significant transparency to the process, because unlike directly using generative AI, as I said, which is a black box, we break down the problem into manageable parts and the predefined tools are used to solve problems. And going to the next slide, really quickly, what are the key components of a React agent? You might have seen this before, but just to have a quick high-level overview, there are a few components that are pretty important in terms of a React agent. One is the memory. When we submit a query, as I mentioned, the query itself will be stored in the memory, as well as the set of instructions that's been provided. So that instructions are typically stored in what we call it system prompt. So we have a system prompt and we have a user query that's been stored in the memory. And every time that we go through this loop, we are going to keep add to the memory. So the memory is going to expand. So that's why the agent always remember what was going on in the past. And we have the memory. So based on the memory, so at this point, the large language model split the problem into smaller pieces on the tout section, and then it tries to go through this loop to tackle each sub-problem one by one. And the way it does that, it will map it to a specific tool, and then it will execute that tool, and the result of that execution called observation. And both the tout and the observation will be stored back into the memory. So, and we go through this loop over and over again until we get to the point that it no longer needs any additional tool to solve the problem. And that's where it returned the final answer, which is a coherent answer that's been generated based on all the information that's been stored in the memory. So that's like a quick overview of the React agent. But now, as we promised, let's explore an exciting application. I'm really, really excited about this. I've been wanting to do such a thing for some time, and I'm glad finally we got a chance to do that. In this demo, we'll showcase how AI agent can streamline and optimize engineering tasks, such as performing parametric studies or sensitivity analysis. And in order to do that, like in the previous slide we mentioned, we need to define tools for the agent, because we don't want the agent to use its training data. We want transparency, we want accountability. And because of that, we want the agent only to use our tools. So these are the tools that we define. So in this case, those tools are one, Abaqus, which is a finite element analysis software. That's a commercial software, but the version that we're going to use is a free version. The license allows for using individually and using for educational purposes, but it has some constraints. But it basically works well for our purpose. There are three tools that we have defined. One is to generate an input file. The input file is effectively your model, the model that you generate. And what this tool does, it runs this script, which is, so first you need to install Abaqus locally. And then once you have it, then you can just run like the way that you run with Python, you can run with Abaqus. And then it will run that particular function. So what this function is, so this function is a Python version of your model in Abaqus. I'm not getting into the details and don't want to make it very technical, because like some of you may not be familiar, and I want to keep it as inclusive as possible. But this is the CAE, or this is the graphic user interface of Abaqus. And in order to generate this create input file, what you need to do when you are creating your model, you just need to go to the macro manager and you just need to create one macro. What this does is that during your interaction with the graphic user interface, is going to store the equivalent Python code associated with every interaction or every action that you do. And this way you can finally have like a code that every time you run that, it's going to generate that model for you. So I'm going to quickly also show you. I've already gone to the repo at the beginning, but I'm going to do that one more time for those of you that you have joined a few minutes later. So you simply go to my GitHub, to the repository, to the first repo, and that's where you see the source code. And the tools that we're going to talk about today are under this RC, the source. and this is the tools. That's the first tool, generate input file, and it effectively runs this script along with other stuff. And this script runs the create input file. So the create input file, this is under utils, and this is this kind of file that's been generated by the macro when you are interacting with Abaqus. So enough about like a technical conversation, but let's go to the next tool. The next tool is that once we have the input file, we have the model. Now we want Abaqus to run that to generate our result, because we have created the model. We want Abaqus to do something with the model and generate something. So that's what this tool does. And effectively what it does is that it goes and run this command. And this time it uses the input file that we have already created, and we just give it a name. We call it like cantilever beam because this is a cantilever problem, and we run that. And once it's been executed, it generates an output file. That's where our like desired output is going to be stored. And when we have that, we're going to run another tool, which is to extract one Mrs. stress. And that's where, when we run this tool, it's going to run this script. And this script, which has the retrieve one Mrs. stress.py, is going to go into the output file .odb file and extract the stress. And then it's going to basically store that in the memory. Just very quickly to show you what this looks like. This is also the function that you need to do when you run that with Abaqus. Abaqus is going to understand this package, and it's just going to go into the .odb file, and it's going to grab the information you're looking for. In this case, we're looking for the maximum one Mrs. stress, and then it's going to return that to us. But that was pretty much it on the technical and the intro before getting to the demo. We have 3 tools, and we are going to make it available to the agent. And then it's up to the agent to run them sequentially or in any order in order to solve the problem that we defined. So now let's go for the demo. For the demo, I'm going to deactivate my my environment. Basically, in order to run this demo, you need to run that locally. So first you need to clone these repositories, then you need to install this requirement, which includes all the packages that you need. Then once it's been installed, you need to go to the virtual environment that you have installed, and then you need to activate that. Let me activate that in here. So I'm going through that because you will have access to this recording and you can just follow along as I'm doing. And then what you need to do, you need to run a Streamlit, run app, and what it does is going to run the Streamlit app that we require here. This is effectively our demo, which is going to initialize and trigger the agent. Like I mentioned, these are the tools. It's a little bit of introduction that we already went through. We don't want to just talk about them again, but these are the 3 tools that's available. I mean, each tool has also some other function that it utilizes, but at the high level, we have 3 categories of tools. And then we have a problem. That's a simple problem. The main goal in here is to understand how the agent works. And the problem is a cantilever beam that's fixed at one end, and on the other end, we just push it downward. And so the displacement or the amount, the magnitude that we push it downward is variable because we want the agents to do some analysis for us. And the cross section is a pipe. It has a 1.5 centimeter of thickness with about 30 centimeter of diameter. And yeah, with that, we can also change the model type. For now, we can use GPT-4o. This is a very inexpensive operation, like a fraction of cent every time that you execute that. So GPT-4o should be good, but it should also work with GPT-4o mini. And here, first, let's go with the easiest problem. At the beginning, we just want the AI agent for this cantilever beam that we basically have already predefined the tools. I want to retrieve the maximum one Mrs. stress when the pipe is displaced downward by 2 centimeters. So what this model, this agent needs to do is needs to use this tool and needs to pass this argument, which is 2 centimeters. I mean, now we have defined one argument. Let's imagine we can have tens or like several arguments. And then it needs to run the model and go and grab the maximum one missile stress. And now we have submitted the query and it's doing its thing. And as it goes, it should give us the progress so that we see what's happening. So this is a progress. We can basically follow along, and at the end, it will show us what are the intermediate steps that it has gone through in order to generate the result. The first step was to basically generate the input file. Then it basically ran the Abaqus in order to run the model, and then it basically extracted the maximum one missile stress. And this is the final result based on it's a coherent answer based on what was generated in the previous step. So the final answer is the maximum one missile stress on the cantilever beam with a downward displacement of 2 centimeters is 13.65 megapascal. Excuse me. The process involved generating an Abaqus input file with a specific displacement, executing the simulation, and extracting the stress data from the results. And the sequence of that, everything has been managed by the agent. Nothing has been hard-coded. This is just the agent figuring out the whole thing. But more importantly, that's the reason that we're interested in, because we want to make sure that at the enterprise level, in our engineering task, it's accountable. We can see what was going on, how it concluded to that result. So this is a reasoning part. The agent says that, okay, I need to generate an Abaqus input file with a specific applied displacement, execute the Abaqus job, and then extract the maximum one missile stress. Again, this is what agent came up with. We didn't say that, we just provided the tools. The agent, based on the tool description, based on the function signature, it's able to find out how to run that sequentially. And it runs this tool, the Abaqus input file generator first, and then this is the result of execution of that tool, which is stored in the observation, as I mentioned before, and the input file has been generated successfully. And then on the thought, now that I have the input file generated, I need to execute the Abaqus job. So it's going to execute the job based on this input file. This is the tool, and this is the observation, which says Abaqus job has been completed successfully. And then it says, with the Abaqus job completed, I now extract the maximum one missile stress from the output database. In this case, this is just the .odb file. It runs this tool, and it goes and grabs the maximum one missile stress, and now it has all the information. It's going to put them all together, come up with a coherent answer, and this is a coherent answer that is going to generate. I've successfully retrieved the maximum one missile stress. The maximum stress with a downward of displacement of 2 centimeters is this. And this is like a little bit of the brief introduction of what was going on. But now that we got familiar with how the process works, we want to now look into the back end. We want to see like how the whole thing works. I mean, this is just the front end. This is very pretty, but we want to see what was going on in each step that it was running. And for that, we want to add a little bit more complexity. We want to tell to the agent that after finalizing this step, I want you to incrementally increase the displacement until the one missile stress reaches the 100 megapascal. So we give it a threshold. We also want it to just go into the loop and keep running that. And then not only that, we also wanted to adjust the displacement increments to optimize efficiency and minimize the number of required simulations. So let's say that if it needs to increase the displacement, how much it needs to increase the displacement. So typically in a simulation, we can set some logic to be efficient, but when we have an agent, this could be the most efficient way of performing that, especially if your simulation is going to run for hours or days. This way, the agent, if you are asleep, if it's like 2 a.m. in the morning, is going to get the result, what's been generated, and it's going to come up with what would be the next step. And that's what we want to see. So I'm going to go ahead and run that. But this time, what we want to do, we want to just go and look at what's going on the back end. So on the back end, it has a nice interface that's been provided by Llama Index. That's where we can see what's happening. So what was the first step? The first step was, so it starts from, let me see, I need to start, I've successfully the max. I need to see what was the initial phase, but it's basically just running and going through each step. And every time that it runs the Abaqus, you see that these input files are generated and are then being moved back in here. And it's going through, you see that these input files are generated and then are removed and then basically moved into the Abaqus file. This is what's happening every time that it's running that. And what this does is that Abaqus job completed successfully. One misses stress is retrieved, and then once it grabs the one misses stress based on how much was the stress, it decide on what would be the next displacement, and then use that displacement, generate another input file, run another Abaqus, and then grab the one misses stress again. So as you see that at this point, the stress is 81.92 megapascal. And then it uses another displacement, which is 12 centimeter in here. And it reached now to 95. And this will be very interesting to see that as it gets closer to the 100 megapascal, it just decreases the amount of change so that it doesn't pass significantly over the 100 megapascal. And then it goes to the 15 centimeter, it generates the input file, run the job, and grab the one misses, which basically is very close to 100. It says that the one misses stress has reached 102.4 with a displacement of 15 centimeter, which is slightly above the target. This is a satisfactory result for the analysis. So that's very interesting.
So that's pretty amazing because you did not condition this agent to perform those steps beyond just giving it the directive of the base parameter.
Yeah, exactly. Which is the reason that it can do parametric static sensitivity analysis and streamline so many tasks that take a really good chunk of time from a lot of researchers and engineers. So if you want to go and check out the step that it went through, we can do that in here on the front end. The thought was this, like before, first it goes with the 2 centimeter. And on the next step, when it grabbed the initial one misses stress, it says that the current one misses stress is 13.65. And the display with this displacement to reach to 100, I will increase the displacement incrementally. I will choose a larger increment initially to approach the target. So this is fascinating. I mean, we have an intelligence in our loop to decide what would be the next step, and that's fascinating because typically all these are like a static like logic that we put in place in order to decide what would be the next step. But now it's like somebody is there and make a decision. Sorry, Mike, you wanted to say something?
Yeah, no, just building on your point, like this, to write as a software developer, to write code that would cover all these conditions and whatnot, there'd be, as the number of parameters and whatnot increases, the number of logic steps would increase and checks and everything else. Whereas in this case, the agent was able to determine these aspects and changing the increments and whatnot on its own. Oh, I see a question. Do the stored memories change as new inputs come in?
Yeah, that's a good question. I'm going to answer that in a little bit because I'm going just to finish this thought. But yeah, this is a great question, and that's very interesting. So just real quick, I wanted to mention that like this is pretty smart and intelligent, and as it decides on just choosing like a larger one. And for now, it goes with doubling that. So you see that, I mean, 4 centimeters is still a small, but it's double the size of the previous one. And it uses the double in order to generate the input file and goes on and on. We will look at the next step, but I'm going to answer the question because it was brought up and that's very relevant. So in terms of the memory, so of course, when we are in one transaction and every output that's been generated is going to be stored back into the memory so that the agent can generate a coherent answer. But the good question, this question says, what will happen if the user asks a new question? does the new question will also remember the previous transaction, or is it going to override that or not? So typically LangChain has solved that. I haven't done that in Llama Index, but LangChain and Llama Index are basically like a competitive like packages that they streamline and abstract out some of these complexities of agentic workflow. And they provide a unique identifier for each one of these transactions. And this allows for that transaction to be a standalone and to be manipulated in the future. And these transactions also to probably interact with each other. This allows for multi-transaction to communicate with each other and to be a standalone and to be run independently. But this is one of the interesting areas when we go into the advanced agentic workflow. That's where we also want to bring the human in the loop. And at some steps, once the agent has run and has done its thing, maybe it took about 5 hours to finish, we want to get in there and we want to go and what was happening in 3 hours after the execution, we want to change something. And that allows us to do that. That allows us to go and inject into the memory or just modify something and run it from that point forward. These are all the capabilities and flexibilities we can get from these agentic workflows. So I'm not sure, Mike, if you want to add anything to that. If not, I'm going to just continue. Okay. And yeah, hope that answered your question, Michael. If not, please just put down on the chat follow-up question and I will explain more. And yeah, as it chooses the 4 centimeter and it generates the input file, it goes on. And this time it gets to the 27 megapascal. And this time it says, to continue approaching, I will increase the displacement by another 4. So this time it increases by another. So this is what's been decided by the agent. And again, all the sequences, everything has been done by the agent. And then it goes on and grabs the result, which is 54. This time it adds another 8 centimeters. So this time it doesn't, it goes from 8 to 12. It doesn't double that. So it's not like a static logic. So every time that you think about that, what would be the best choice and do, so increase that accordingly, it get to 81. And this time it says that I will increase the displacement by a smaller increment of 2 centimeter and we will get it to 14 centimeter. And this gives us 95.557. And it says now we are very close to the target. I will increase the displacement by a smaller even. So 1 centimeter. Let's get to the 15 centimeter. And it does that. And it gives us the 102, which is pretty close to 100 megapascal. So we can also refine the query and we can make the agent to be a little bit more cautious in terms of like what it does in terms of the increments. And our instruction was very general and broad, but still it did a great job. And yeah, the warm stress has reached 102, displacement of 15, which is slightly above. This is a satisfactory result for the analysis. And then based on what was going on, it provided a coherent answer, incrementally increased the displacement 4, 8, 12, 14, and finally 15. One misses increased to 102, and the target one misses was reached with a displacement of approximately 15 centimeters. Yeah.
So then you can also imagine taking this and hooking it up to a report writing agent.
Exactly. So that's what we were talking. That, I mean, this is a super easy example. Typically, a kind of problems that we solve with numerical analysis is not like that, because that could be also solved analytically. So these kind of numerical simulations, I mean, some of the more complex numerical simulations, some of them take hours to run, even with clusters. And during that time, every time that it generates a result, that result could be fed into like another process or into another agent. So that's what we call it like multi-agentic workflow. And that agent could just get started on just writing down a paper or just drawing a graph and just keep updating that graph, etc. And that's what you, Mike, I believe, was referring to. And that's very cool. Change. So there's another question: do the stored memories change as new inputs comes in? So we have the So this system that we have defined in here, it's been developed to handle one only single query. Every time that you run a new query, it's going to override the whole thing. It's not going to remember the previous transaction. So in what we have developed, because this is just a demo just to showcase the capability. But there is a possibility and flexibility that whenever you have an interaction, the new input doesn't override the previous input. And it can just keep adding to the memory so that the agent, based on its context window, some of these new large language models has a very a significant context window, but based on its context window, it can remember everything that was going on in the past. And in these typical problems, we are not going to feed a significant amount of information. It's not like a retrieval augmented generation that we want to feed a few paragraphs of a guideline. This is pretty a small number of tokens. So it can remember so many things or so many conversations in the past if that's required or that's what the business needs. Anything to add on this, Mike?
Looks like we got a couple of questions. Agent comes to its result. So seeing how the agent comes to its result, what does this mean to the overall enterprise system? Well, I think there's a couple things. So one would be is that once this type of a pattern is set up, so using this type of numerical analysis, finite element analysis tool that Farhad is showing you behind the scenes, they're fairly complicated. So a senior engineer who understands this domain could set up a process like this and then make this available in ways that were really not possible before, while still having the agentic control around the running of the actual analysis itself. So then you either have junior engineers doing these types of things, or even people who may not necessarily be fully versed in the operation of these types of tools, but could still execute a run like this to get design insights in ways that were quite difficult before. The other thing that these things that Farhad has also demonstrated, I think, in the past session, but handling unit conversions, different types of inputs that may not be in specific alignment with the inputs required by the model, the engine or the actual finite element analysis system itself. The agents are smart enough that they understand the fact that these tools have been conditioned to take specific types of unit bases and whatnot, and they can do the translation of the units across to match the required inputs. The other thing would also be coupling different systems together. So if you've got a groundwater numerical modeling system that does contaminant transport flow, and you have another one that's doing, actually a better one might be the case of having a pipeline going through permafrost where you've got ground conditions and there's a type of numerical models that govern that domain, and then the pipeline deflection, the deflection of the pipeline that goes on top of it. You could have two different models doing the finite element analysis associated with heat transfer from pipe into ground, melting ground, causing pipe to deflect, stress analysis on pipe as it deflects, and have those two models work back and forth to optimize the design of that, this sort of thing. And then, of course, the report writing piece. You could actually have an agent that would pick up the outputs of this and generate a baseline report out of it, that then could be presented to an engineer for verification, checking, and other things before it was stamped and whatnot. There's all sorts of really, again, shortening the design times and the things required, getting data as inputs for these things from different places. That whole process of assembling the data and whatnot could be, if you can imagine having agents that are hooked up to Revit, up to other types of databases and whatnot that are required to pull together the data for the inputs to these types of models is another place. Then the engineers aren't having to waste their time digging data out of things. Farhad, any thoughts there?
Yeah, you covered that well, and this effectively goes back to what you initially discussed and presented in this, at the beginning of this presentation, that whenever there are a few tools that they need to communicate with each other, that where the agent can streamline the process. For instance, anything also could be defined as a tool. When we talk about tool, it's not just Abaqus as a tool. Just going through a design guideline could be defined as a tool so that we have the agent to parse the design guideline and it can execute different sections of the pipeline. Let's say that you have a report, you have calculation, and you can run it by the agent so that agent could go through like a different guidelines or like whatever guideline that's been needed, and then validate the result that's been generated. Or any other process that requires several tools to communicate with each other. That's where the agent could play an important role. And another thing would be what we discussed in the previous session. There are so many scenarios that access to the senior engineers is limited because those subject matter experts, they're pretty busy. And some of them, they have 30 years of experience. And if they retire, like all that experience is going to go with them. What the company could do, they can feed all that information, all the meetings, everything that's been generated by that individual, or all his knowledge, the majority of his knowledge that's been used in different works, etc. It could leverage that and it could just document that, and that document could be available to the agent. So that agent could act as that, like a senior like engineer that could help the junior engineer for onboarding, for like validation of the calculation, and for so many more. It's just like we can be so creative with these agents. Yeah, I mean, we get very excited about these questions, and I mean, I personally talk a lot, hopefully. Yeah, knowledge transfer. Yeah, you basically summarized the whole thing very well. I should have said that. Nice. Awesome. So we have got to 1 p.m. Thank you everyone for being with us for another session, and we will see you sometime in January. Stay tuned and follow our channel on LinkedIn, where we're going to post about our upcoming session.
Yeah, make sure you check out the source code libraries and whatnot. This is the code from these sessions we are publishing, so you can check it out.
Awesome. Thank you, everyone. Have a great day.